Okay, so the question is a regular pentagon with a size of length 10 centimeters and radius of 8.5 centimeters has a charge at each vertex. These are the vertex, by the way. What you see is a pentagon. Four of the vertices have charge of 30 microcoulomb and one has charge of minus 11 microcoulomb. What is the magnitude of the electric field at the center of the pentagon? So this is the center. So let's put these four charges into these, right? Okay, let's pick up this one, and this is 30 microcoulomb, and put over here 30 microcoulomb, and put over here another 30, and over here just another 30. So the last one, let's pick up this one as the last one, as minus 11. Let's put over here minus 11 microcoulomb charge. So the question is, well, let's put also the dimensions, that the side length is going to be 10 centimeters, or let's put 0.1 meters, and all of these sides 0.1 meters, and it has this also the radius, that each one of the charge, if you think about this distance as the radius, has the distance to the center, which is 8.5 or 0.085 meters as the radius. So the question is, what is the electric field right at the center? So for these kind of questions, all of the charges are point charges, and if you need to calculate the electric field at a particular point, what you do is just calculate the fields one by one because of each charge by using the electric field uh, formula expression, kq divided by r square, and add all these expressions as vectors at the center, at the particular position. So let's think about what kind of electric field is going to be. That this one will produce an electric field in this direction, this one will produce an electric field in this direction, and this one is going to produce electric field in this direction, and this one produce in this direction, and this one produce electric field towards the charge because it's minus in this direction. And there is going to be a total of 5 vector to be added as vectorially. And also there are angles in between, etc., etc. So but there's a trick to find the result of such questions very easily. The trick is that, well, think about this, all these 30 micron charges at these vertices, okay, 4 vertices. What if you put also at this vertex at the same charge 30 microcoulomb plus 30 microcoulomb? Think about this, replace this minus 11 microcoulomb by 30 microcoulomb, 30, 30, 30, 30, all of the 30. So what is going to be electric field at the center? Well, obviously it's going to be 0 because of the symmetry, right? And all these fields, all these point charges have the same distance to the center. And, they will produce the electric fields of same magnitude, which are all directed towards these 5 corners, 5 vertices, and the angles between all these electric fields are going to be the same. You just divide 360 by 5, and obviously in that case the electric field at the center is going to be 0 because of the symmetry, right? 30, 30, 30, 30, 30. They will all produce non-zero electric fields, but if you add all these electric fields at the center, because of the geometry of the problem and the symmetry of the problem, the electric field is going to be 0, right? So, but it's not the case. What you can do is, well, you put 30 microcoulomb over here, and in order to have a net minus 11 microcoulomb charge at this vertex, instead of this, you just put minus 41 at the same position. So at this vertex, on top of each other, there are two charges. One is plus 30 microcoulomb and the other is minus 41 microcoulomb. But the sum of it becomes minus 11 microcoulomb, which is the original problem that this vertex must have a minus 11 microcoulomb. But instead of writing minus 11 microcoulomb, assigning only one charge over here, let's assign two charges over here, and they are on top of each other, and one has 30 microcoulomb charge, the other has minus 41 microcoulomb. But if you add these two charges, it's going to be minus 11 microcoulomb, so which is going to be the original problem. But the thing is, the reason that I do this addition of replacing one single charge of minus 11 by two charges of this quantity is that to further use the symmetry of the problem, so that 30, 30, 30, 30, 35 of these 30 microcoulomb charges would have a net electric field of 0 at the center. So you just eliminate these 5 charges and you are left with minus 41 microcoulomb, which has a certain distance of 0.085 meters, and just calculate the electric field created by this minus 41 microcoulomb charge. That's it. So this way you don't need to calculate the resultant electric field of 5 different electric field vectors by just calculating the angles between them, etc. So you don't need to do this. You only require to calculate only the electric field of one single point charge, because of the symmetry, these 30 microcoulombs will produce a 0 electric field at the center. So I hope that you get the idea. So you are only left with then, at the center of the electric field, with this distribution of charges, the electric field is going to be just toward this vertex, and the calculation is going to be like 9k is 9 times 10 to 9, and q is minus 41, but just we're calculating the magnitude, 41 times 10 to minus 6 coulomb, and divide this by 8.5 squared 10 to minus 4, because we need to take the square of the distance, etc. So if you do this calculation, then what you find is 5.1 times 10 to 7 Newton per coulomb as the magnitude of the electric field. Sorry, let me put this over here. 10 to 7, yeah. So this is going to be the strength of the electric field at the center of the pentagon, and with this configuration, which is upward, and Newton per coulomb. That's it. This is how we solve the problem.